This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, good morning everyone. Let us start. This lecture was last year a single one, but I thought it normally takes more than 1 hour, so I split it into two. Okay, and we are a bit delayed, so I'll try to compact it back. Okay, so we are working on principal access, and today I will show you kind of two things that you need to remember. First is how to find principal access, all right? And with that comes the meaning of what that means, principal access. And also I will show you how to convert the inertia tensor from one frame to another frame, all right? So you need to understand that one as well and use it correctly. So as you can see here, for the cuboid here, I have these red axes, and they are kind of special ones. And what's special about them is that if you are choosing your coordinate system, let's say G or B or whatever, as long as that coordinate system is parallel to this one, drawn here with all the axes normal to the faces of the cuboid, then the result will be that your inertia tensor will be diagonal. Remember, I already showed you, choosing something like that as the axis, we got a diagonal inertia tensor. Okay, so I will show you why do we need a diagonal one. Okay, so in this motivation example, remember, you want to understand why do we care whether or not our inertia tensor is diagonal. All right, why do we want a diagonal inertia tensor? And then we'll go to how to find the specific coordinate system or axis or principal axis in which the inertia tensor is diagonal. Okay, so this is the following step. And then I will briefly discuss whether it's possible for all shapes, right? And then I'll show you some examples. All right. So for the motivating example, I keep that cuboid because it is very intuitive to kind of understand where the principal axes for that cuboid are. So the scenario is like this. This cuboid has a hole passing through it, and it is mounted on a shaft. All right, the shaft is, let's say, steel, and something is rolling that cuboid around the shaft. All right, and let's say the roll is with a constant angular rate of change, omega. About this axis, which I define, say, as y0, and I also attach this red coordinate system G to the cuboid. So as the cuboid rotates, this red frame G rotates with it. All right? Now, we already discussed the inertia tensor for such a cuboid. So in the red frame G, in the body fixed coordinate system, the inertia tensor is diagonal. We saw that if you try to calculate from the definition using the integral, the products of inertia, so the elements outside of the diagonal, you will get zeros. Okay? If you choose your axis to go normal to the faces. Okay, so within this choice of axis of the coordinate system in which you calculate the inertia tensor, if they are normal to the faces, we received a diagonal inertia tensor. Okay, I hope you are convinced. If not, go to the lecture about inertia tensor about center of mass. we had a diagonal result there. And now as this cuboid rotates, we have here the rotation matrix between the from the red frame G to the black frame 0. Okay, and this is positive rotation. You can look at the direction here, kind of the gray arrow behind the red arrow. Okay, so positive rotation about Y. Okay, so the YG and Y0 are aligned. Okay, this is the scenario, pretty simple. What I want to find, or let's say I want to construct the Newton-Euler equation, the angular one, the angular Newton-Euler equation for this cuboid, because I want to find out what are the moments that should be applied on that cuboid for it to perform this motion with a constant omega. Right, so in order to construct the angular Newton-Euler equation, which we've discussed, it's the sum of moments equals h dot, h being the angular momentum. We will first need to construct the angular momentum, h. Okay, so h we said could be found by I omega, where omega is the absolute angular velocity of the rigid body. Okay, so we need to find h, then take its derivative to find h dot, then we get the resultant moment that has to act on this cuboid to perform this motion. All right, so I will be doing the same thing later, where this cuboid is mounted differently on the shaft. I will do the same procedure, and you will see that the moments that have to act on the cuboid are different. Okay, so I'll get there. Is it clear so far? All right. So in order to calculate, so the bottom one is that Newton-Euler equation, the angular equation, h dot equals sum of moments, and this is h as I omega, and I calculate it in the red frame G. So in the red frame G, this is the diagonal inertia tensor, and the absolute angular velocity of the cuboid, just omega in the YG direction. Okay, so the product is here. You can look omega times the YY component. All right, so this is h, the angular momentum of the cuboid as it rotates with this constant angular rate of change. And this is h dot. So I'm using the golden formula per normal. Now this omega is constant, and this IYY is some kind of constant depending on the dimensions of the cuboid. So because this is constant in frame G, this h prime, the component by component derivative, is all zeros, right? And this is the absolute angular velocity of the frame in which I take the derivative, which is G. Now frame G rotates with the same angular velocity as the body, so like that, all right? And this is h itself, so omega cross h. And because they are pointed in the same direction, that YG direction, the result is all zeros, okay? This is important. It means that I don't need to apply any moment to have this cuboid rotating with a constant angular rate of change about this shaft. So once it started rotating, it can keep going. All right, keep going with the same omega, nothing special. Okay, this is important because it means that if there is no moment that I need to apply on the cuboid doesn't try to rotate the shaft. Okay, so the only moments applied on the shaft will be as a result of gravity. Sorry? Sorry? Someone said something? All right. Okay, now what I want you to notice is the special case of zero moment applied on the cuboid to preserve this motion happens because our vector of angular velocity is parallel to the vector of angular momentum. Angular velocity of the shaft is parallel to angular momentum of the shaft. And this happens because, essentially because the inertia tensor is diagonal, like that. So what happens if it's not the case? So let's look at a different mounting of this cuboid on the shaft. So now, let's say you don't know how to align the cuboid appropriately. Now this is very exaggerated, but imagine if you have a part that you want to mount on a shaft without the shaft wobbling. You want to mount it kind of correctly without having extra unneeded moments on the shaft, right? So this is the motivation for finding the right orientation, the right directions. Maybe for a cuboid it's straightforward, but what if you have a very weird, odd-shaped part and you want to mount it correctly on a shaft to rotate? So you will need to find these directions. But if you don't know, let's say you mount it like that, very unaligned. Now this red frame G, just like before, it keeps rotating with the cuboid. It is attached to the cuboid. Alright? So the red frame is just like before, with the same R from G to 0, alright? Same rotation matrix. It's just that the cuboid, its orientation relative to this red frame is different. But this red frame is still a body fixed frame for the cuboid. And if you calculate the inertia tensor relative to this frame G like that, yeah, so your integrals here will have different limits of integration, you will get some non-diagonal inertia tensor. Okay, so having the orientation of frame G like that with respect to the cuboid will result in your inertia tensor in this frame being non-diagonal. Right? You can try later. So what that means, here I'm calculating H again and H dot again for the angular Newton-Euler equation. So H would be I omega, omega of the cuboid, which hasn't changed. It is still this omega about YG, all right? It hasn't changed. It's just that now, because this is not diagonal, H, the angular momentum, is no longer parallel to the angular velocity. So at any given moment, your angular velocity of the cuboid is still about this YG, but your angular momentum is not. And this is due to some uneven distribution of the mass. So as you are mass of this cuboid, yeah, as you are rotating the cuboid about this YG, it's like you get some components of the cuboid trying to fly in the ZG and the XG directions. Okay, so because of the mass distribution, the angular momentum is no longer parallel to the angular velocity. And as a result, this cross, yeah, this is still application of the golden formula. Now, this is all constants. So when you do the prime, it will still become 0, the prime part. So you are just left with the cross part of the golden formula, angular velocity of frame G cross product with H itself gives you this thing which is no longer 0, right? So you have this component here which is, well, it depends on YG, on I, YZ, essentially, I, YZ. So because the mass distribution in the YZ plane is not symmetrical with respect to this X direction, there will be some moment that has to be applied on the cuboid in the X direction to keep this motion. Okay, essentially without the cube detaching from the shaft and flying away. And here XY, so because of mass distribution not being balanced about the Z direction in this XY plane, so there will be a moment about Z that has to be applied. Now, who applies this moment on the cuboid? The shaft, right? If the shaft has to apply this moment, then the opposite moment will be opposite sign, let's say, but same magnitude would have to be applied on the shaft by the cuboid. Okay, and because of this moment applied on the shaft, you will see, if you look at an experiment, you will see that the shaft starts wobbling because of the bending moment, okay, in the X and Z directions. So this vector here has some constants in the XG and ZG directions, but these XG and ZG directions, as the cuboid rotates, they rotate, right? So they will have every time a different component on the X0 and Z0 direction. So if you're standing in the lab, once your moment will be in that direction, then that direction, then that direction, and it will go around. That's why you will have this kind of wobbling that goes around for the shaft. All right? So the important bit here that I want to stress, because the inertia tensor in this coordinate system G is not diagonal, what we end up having is we don't know the direction in which we can put a shaft such that it won't wobble. Okay, we can't guess it like that, right? If we know that the inertia tensor is diagonal, then we can choose any of the axes that are parallel to that frame G and mount a shaft there, and it will rotate without wobbling. Okay, it will be smooth. So the result of this moment being not 0 goes back to this being not diagonal. All right? So this is the motivation of why do we want to have a diagonal inertia tensor. Okay, and part of that is, can we find it? And if we can find it, we need to know the axis, essentially. We need to know how to orient correctly the red axis, the body frame axis, relative to the body itself, so that these are the right directions where the inertia tensor will be diagonal. All right. So before we move on, I want to do some simple algebra to demonstrate this formula of how to transition from inertia tensor expressed in one coordinate system to inertia tensor expressed in another coordinate system. Remember, inertia tensor is not a vector, so it's not simply like we are doing for vectors, multiplying by rotation matrix. Here you will see that we need to multiply by 2 rotation matrices from both sides, yeah, the opposite ones. So I just want to go through this slide so that you kind of digest this idea, and then we move on back to finding principal axis. So what I'm doing here, essentially, I'm utilizing the idea of rotation matrix for a vector to move from the angular momentum vector in one frame to the angular momentum vector for another frame, sorry, in another frame. Okay, so how to do that? Here I have some angular momentum h in, say, frame A, okay, which is I omega all in frame A. Okay, this is valid. And similarly, I have h in frame B, which is I omega all in frame B. All right, and now this part is using the fact that h is a vector. So instead of h in frame B, I can write h in frame A pre-multiplied by the rotation matrix from A to B. Okay, so from here I kind of skip to here. Is it fine? And now instead of HA, I will substitute this. Okay, so this came here. And once more, instead of the vector omega A, I can use R from B to A omega in frame B. Okay, so this thing here must also equal this thing here. Okay, so this one is I in frame B times omega in frame B, and this is some other matrix times omega in frame B, from which I conclude that this triplet here is I in frame B. All right, so this is the simple proof for why it works. So if you need to convert inertia tensors between different frames, this is how you go. Okay, you just need to know the rotation matrix between these frames. And how to assemble it, just how to remember it. This is how I remember it. I start by treating I as if it were a vector. So if you ignore this bit in your mind, you have like I B equals I A, rotation matrix from A to B. Okay, so this part is kind of familiar. And here you plug in the transpose of that. Okay, so if this is R from A to B, this is R from B to A. Okay, so easy to remember. Okay, so given that, yeah, that I can transition from different frames, let's say, let's say I have some rigid body, yeah, and let's say I know the inertia tensor relative to this red frame, okay, and I am trying to look for a specific coordinate system where the inertia tensor is diagonal. Okay, so let's say I try one, okay, I try a different one. I will, using this formula, I will know how to transition from I in the red frame, let's say the red frame is R and the green frame is G. So having I in frame R, I know how to find I in frame G. Okay, and I know how to find I in any desired frame. Okay, so the question that follows is, can I find some kind of best friendly frame? I'll call it D, despite the color. D for diagonal. So can I hit a frame where ID is diagonal? So has some components here, okay, and the rest is all zeros. Maybe I should be clear. Yeah, so this will be some kind of I x x, I y y, I z z. So can we find a frame D such that I in that frame is diagonal? Okay, so the answer is yes, we can. I will explain why soon. We will find it, we will be able, so given any kind of guess frame, R, let's say, we will be able to find this frame D in which I is diagonal. And we will, of course, be able to find this I as well, because now we learned how to transition from one frame to the other. All right? So this is where we are going to, and what I'm looking for, having this diagonal inertia tensor in this magic frame D, okay, that I claim exists, or let's say at least so far we suppose exists. So what happens when we work in this frame D? As we saw in the beginning, if you rotate the rigid body, or if the angular velocity of the rigid body is in one of these directions of the axis of frame D, your angular momentum will be parallel to the angular velocity. So in this, let's say the first equation, what do you have? It is angular momentum, h, which is I omega. Yeah. So you are equating here h, essentially. And I, being diagonal, if it is multiplied from the right by an angular velocity vector, which is purely in either x, y, or z of these axes of frame D, the resulting angular momentum is in the same direction. Okay, maybe I'll go back here. If I'm working with these blue axes, yeah, so let's say if this is xd, yd, and zd, if body, this is body B, okay, if body B has absolute angular velocity, so let's say omega B, in frame D, just about this xd, so let's say omega 0, 0, something like that, then h in the same frame D, yeah, will be, if I need to multiply I and omega, it will just be Ixx times this omega in the first component, Ixx omega, and zeros in the rest, okay, if you perform the multiplication, okay? So what we get is that this and this are parallel. And they are also parallel to this xd axis, which is one of the principal axes. Okay, and you could do the same for y or for z, d, y, d and z, d, right? Okay, so this is the idea. The vector omega, if it is parallel to one of the principal axes, I will go a bit forward. If the omega vector is parallel to one of the principal axes, and here I'm talking about the absolute angular velocity of the rigid body, then the angular momentum will be also parallel to the same principal axis. Okay, I'm chewing this idea because I'm going to use it. So remember this kind of parallel. And for vectors to be parallel, it's simply that one is a scalar times the other vector. Okay, so this is where we are going. One vector is a scalar times the other vector. Now we don't know the scalar yet, so I put it as lambda. I suggest you don't need to read the things in the boxes, you can just listen. So what we had in the previous slide, I'm just combining all of these equations. These are three cases. First case, if omega of the rigid body is parallel to xd. Second case, if it's parallel to yd. And zd, third case. So I'm combining all of these cases to one equation, I omega. This star means this omega is necessarily parallel to either xd, yd, or zd. Okay, but at this stage I don't know where these xd, yd, zd are. Okay, I don't know even, but I ask myself, could it be a case that I omega, the angular momentum, is parallel, that is a scalar times, to the angular velocity. Okay? So could I achieve these things? So I just put it in a more general structure, okay? And now so I'm looking for this to happen. Okay, I'm looking for something like that to happen, because if it will happen, then I found the right I matrix, okay, and the right kind of directions, okay. And in addition, what is this lambda here? If you look here, if this is omega, and this is your h, okay, the scalar is this ixx if it is omega in the x direction. Okay, so the scalar is ixx if omega is directed in the xd direction. Okay, similarly, if your omega is in the yd direction purely, then your scalar, this lambda, should be the iy dy. Okay, this scalar to move from omega to h. Okay, so from omega to h, this lambda can either be ixx, iyy, izz of that diagonal inertia tensor in frame D. I'm kind of preparing the ground for you to notice that. Okay, so summing up again, this equation is something that I expect to happen when I find my diagonal matrix I, where this omega is the absolute angular velocity of the rigid body, hypothetically directed in either xd direction, yd direction, or zd direction. Okay, if it happens, then I will have this equation correct, which is angular momentum parallel to angular velocity, and the scaling factor between them will be one of those components of I, D. I in frame D. Is it clear so far? Now from this equation, we can easily find these specific directions or frame D. We can find it. Okay, I will show you how and why. Now remember, we are starting without knowing where this D frame is. We don't know at the beginning. We are starting by fixing some random frame A, and in A, so maybe I'll change this. Instead of R, I'll call it A. So let's say we are starting with A frame. Okay, now I'll change that to A. So we are starting by having this, fixing this somehow, and we are looking for that wonderful frame D. Now, this one, I remind you, is not necessarily diagonal, all right? But if the body still has this angular, so hypothetically, if the body has absolute angular velocity directed in one of the axes of frame D, I can also express this vector in frame A as well. I will redraw that. So let's say the rigid body, and this is some random frame A. Okay, and it has its, let's say, XA, YA, ZA axis, and this is the special frame D that we are after. We still don't know how to locate it, but what we know, so if this is XD, YD, and ZD, yeah, so this is, the blue one is frame D that we are searching for. If the body rotates, say, purely about this direction, yeah, so assume, hypothetically, omega of this body B, in frame D is just some kind of omega 0, 0, all right? We can express omega in frame A as well, just using the rotation matrix from D to A, like that, right? So the same vector of angular velocity, this omega of the body, we can express it either in frame D or in frame A, right? It's just that in D it will be omega 0, 0, yeah, with 0 components here, and here it will be all components non-zero, not necessarily, right? And in a similar way, we could do the same idea for YD or ZD. Just keep it in mind. Okay. Now, I already explained that H of this body in frame D should be parallel to omega in frame D. So some kind of, let's say, lambda times omega B in frame D, right? And this H in frame D, I can also present in frame A using rotation matrix. So H of the same body in frame A will be just rotation matrix from D to A times HB in frame D. right? So I can substitute instead of this one, yeah. And I get lambda omega like this. And now instead of this one, I can substitute this one here, okay, but just maybe pre-multiplying this entire equation by the inverse of this one. Okay, so what do I get? I forgot guys to have the I. You should wake me up. Sorry, no, I was fine, sorry. Yeah, I'm fine, but just for you to remember, I wake up during the night every hour, all right? I'm not really fine. Somehow my daughter knows when I need to lecture, and my hope was that she can stay at home and just drink from a bottle, but she refuses the bottle, so I carry her with me. All right. So let me substitute here and see what happens. So dA, and instead of this one, I will put R from A to D, okay, times omega B in A. Okay, so these two things, they cancel out, all right, and I'm left with lambda omega B A, like that. Okay, so again, these two vectors, what I was just trying to demonstrate is that these two vectors are still parallel, never mind in what frame I represent them. Okay, just that if this is the vector of angular velocity, then the vector of h will be parallel as well. Okay, never mind if I represent these two vectors in the nice blue frame where they only have one non-zero component, or in the random frame A where they have all the components non-zero. Still they are parallel. Okay, they are pointed in the same direction in space. All right. So this result here, I'm just going back to the slides. If my magical frame D satisfies this thing, it also satisfies this thing, okay, in frame A. So if this is correct in frame A, yeah, given that omega is in one of these magical directions, yeah, one of the principal axes, if I have this, I'm on the right track to finding my frame D, essentially. Because this omega is directed in one of its axes. Okay, and if such D frame exists, then I have all three directions. So this equation will be correct for three types of directions for omega. Yeah, x, y, z of frame D. Okay, because I can either point my green vector, I can I can write this equation for the green vector being either along xd or yd or zd. So essentially this phenomena happens at least 3 times, yeah, simultaneously. Either this frame D exists with all of its x, y, z axes or not. But if it exists, then we get this parallel between omega and h in 3 different possible directions. All right. So now the idea is to go from. Don't read that. This is just what I did on the document camera. So starting from this, without knowing what omega should be to satisfy this equation, and without knowing what lambda is to satisfy this equation, we can still start from this equation and head towards finding all the directions xd, yd, zd. Alright, so starting from this, I just want you to know that the only thing we know is this I in frame A, where frame A is some frame that we chose. Okay, it's some kind of random frame where we can find our I, possibly in a convenient manner. So what to do? Again, this is the same equation. We start from it while lambda is unknown and omega is unknown. Okay, but we keep in mind that this omega, if we find it, it will be directed. So to satisfy this equation, this omega will essentially be directed in one of the principal axes, and this lambda will be the corresponding inertia, moment of inertia in that direction, in frame D, essentially, in the principal frame. Okay, so from this one, what you can do, this problem is, you must be familiar with eigen decomposition problems, right? So this is how you start formulating this problem. If you shift this right-hand side to the left, you get this equation, and you can take this omega outside the brackets, and what you're left with is some matrix times some vector which is non-zero. You assume your omega is not a zero vector, equals zero vector. That means that in order for this equation to be satisfied, you must have this matrix not full rank, or have it with zero determinant. So you put the determinant of this these lines for me is determinant. Determinant of this matrix has to be 0, and that would depend on the lambda and on the specific values of the inertia tensor in your frame A. What you're doing now, you are essentially working in frame A, and you are working to find this lambda, and such vectors omega for which this thing happens. And as you can guess, if you can find such a lambda, you will find. Okay, maybe let me go a bit differently. Can you find such lambdas for which the determinant is 0? And the answer is yes, because your matrix I that you start with is symmetrical. It is symmetrical because it is an inertia tensor, and by definition it is symmetrical. And because of this symmetry of I, from linear algebra, you know that I is diagonalizable, which means it is similar to a diagonal matrix. It means that constructing this equation for an appropriate symmetric inertia tensor, you will be able to find simultaneously 3 such lambdas, because you will have here a polynomial essentially of order 3. Okay, you have when you calculate the determinant, you will have a third order polynomial with three solutions for lambda. Okay, all of them existing, not all of them real. All right, all of them real, not imaginary. All right, so I guess from here, what you can find is simultaneously three values of lambda, and for each of these lambda values, you will find the corresponding eigenvector. And these eigenvectors could stand for these omegas. Okay, so you are finding essentially three sets of lambda and omega to satisfy this equation, and then this equation, or this equation, yeah, or this equation. So again, by solving this eigenvalue or eigenvector problem, you will end up with three values of lambda. For each of them, there will be a corresponding value of this omega star. All right? And because you are working in frame A, these omega star values will be in frame A. Okay, so I'll just quickly summarize, and I just want to stop in a kind of meaningful place. Right, so we start by, let's say, having some given or self-assigned frame A in which you can find I in that frame A, right? Then you solve I A minus lambda times the identity matrix. The determinant of that equals 0. That gives you three values of lambda, right? 1, 2, and 3. And substituting these lambdas back, you will be able to find corresponding values, omega 1, let's say, omega 2, omega 3. You know that these three omegas are pointed in the principal axis, or in the directions of that frame D. So what is left to do is maybe tie all the edges to convince you that these are the right directions, where the axis will be those axes of frame D, and decide which one will be the XD, which one will be the YD, which one will be the ZD. And also convince yourselves that I in that frame D will be composed of these lambdas along the diagonal. All right, so I'll come back to this afternoon. Thanks a lot. But I is not a vector. Oops, sorry. I is not a vector.
I is 3 times 3 is like
3 by 3, yeah.
3 times 1 is vector.
A vector. Yeah, 3 times 1 is a vector. It's good. You can apply this rotation. Hi, Craig.
So it's got some weird geometric consequences. The fact that any tree shape, no matter what the shape is, it will always
even
have.
if there is no symmetry, there will always be a way to. Yeah, it's interesting.
There will be three axes or three.
Yeah, three directions.
That's right.